Okay, so the difference between, even though we're still in the polar coordinates section, we are moving from coordinates to equations because equations really are made up of a bunch of coordinates, aren't they? So equation conversion uses the same formulas as your coordinate conversion, right? How you go from x to polar, y to polar, and x squared and y squared to polar r squared. Now I want you to remember something we did in the video yesterday. We did this problem. I had you make a table of values for this, and then I showed you on your calculator that we got actually the graph of a vertical line. Let's use our equations and transform them. They want me to convert. So I want to use one of these formulas. I see r is up there, but this is r squared. I see r with a oh wait, isn't this which means what happens if I multiply both sides by cosine? And now, what is this? Oh snap, that's a vertical line where x is always 3. So, can you, and this goes to that matching, right? Can you just look at this polar equation, given what we did here, and figure out what this is? Without converting? Now, you're going to have to convert because I asked you to. But before you do, can you figure out that this is going to also be a line, but it is going to be horizontal, isn't it? I'm going to divide both sides by cosecant. But cosecant, reciprocal identities, trig is so important. 1 over cosecant is the same as sine. And r sine theta is y. Oh snap. That is the equation of a horizontal line. What the hee-haw is this? Right? I don't even know what to do with this. Radius is always theta over 3. I don't know why there's that little mark there. What is this? So my radius is changing, right, as theta changes. Well, duh. I don't quite know what to do with this. I don't have any sines or cosines in the equation, so I can't do that, but I can deal with r, right? What is r? Well, r is the square root of x squared plus y squared, isn't it? So this is the square root of x squared plus y squared. What do I do with theta? Oh, I left off a formula up here, didn't I? Yeah. So this isn't this 1/3 theta? U. I guess I could square both sides to get rid of the radical, but, U. Not much I can do with that. Like, these turned out so pretty, right? And I knew exactly what they were. I have no freaking clue what that thing is. Weird. All right, let me move on. U. Well, I've got a cosine theta and a sine theta, but I don't have a what? Well, let me do a little algebra. Multiply both sides by this whole freaking thing. Whoops, sorry. Now distribute, and what happens here? Oh snap. Hello X. Hello Y. Hello standard form of a diagonal line, right? Vertical when I have only x to the first. Horizontal when I only have y to the first. Diagonal when I have both an x and a y to the first. Right, now standard form, can you tell what that is? Right, if you cover up the y, right, if you make y equal to 0, the x-intercept is 4/3. And if you cover up if you make x 0, the y-intercept is -2, right? So at a -2 and a positive 4/3, this is the equation of a diagonal line in polar form. I don't know what this is, but this is a diagonal line. Now, I started off yesterday's video saying one of the reasons why we want to use polars, perhaps in the future, is that we have a way to represent what looks like a function, what's not a function, in a function type equation where I have an independent and a dependent, right? A vertical line is not a function, but a horizontal line is, right? A horizontal line is a function. So this is swell, but if you're trying to convince me that it would be nicer to be able to represent a vertical line like this, I can at least buy it somewhat, because a vertical line, I understand in function land, gives me issues. But a horizontal line never gives me issues in function world. So I'm not sure why I would need that. I don't even know what this looks like, so I can't make any comment on this other than to say certainly in rectangular form, this does not look pretty at all. Over here, again, if you're trying to convince me that this equation, which ends up just being an algebra 1 diagonal line, I don't really see the purpose of using polars for a horizontal or a diagonal line. But it is kind of cool to know that you can do that. So get your calculator out. Let's look at some of these things on our calculator. Right, here was the one from yesterday, right? 3 divided by cosine theta, that's r equals 3 secant theta, and we got our vertical line. So what happens if you go change that to 3 cosecant theta, which of course is 3 divided by sine theta? Oh snap. There's my horizontal line. Shocker, at what height? 3. Y equals 3. Let's skip that one that we don't know what it looks like, and let's graph this one. Y equals 4 divided by, let's put a parenthesis in there, and then insert a 3 cosine theta minus 2 sine theta, and graph that. Why does it do that weird, like, graphy thingy where it, like, graphed the top half and the bottom half? Hit your window. Theta is going from 0 to 2 pi. So it is plugging in 0 first, right? And calculating all the values from 0 to 2 pi. So What does it do when theta is 0? It's right there. X is, oh, gee, 4/3. Then as theta moves on, you're getting all of these values. 4 comma 4. Gee, what theta is that? Math is cool. But now notice it jumps, right? Where I have a positive x and a positive y. Theta is 0.9. But now theta is more than 1. So notice my x and y are negative. So that's why the calculator is jumping here. Gee, I wonder what y value that y-intercept is. -2, excuse me. Crazy, right? Now let's do that one that we didn't know what it was. Theta divided by 3. Ooh, it kind of looks like a seashell. You know, like one of those spinny seashells, one of those like, I don't know what animal is in it, a conch? No, a mollusk? I don't know. Hey, what if I want it to go further? Instead of going to 2 pi, why don't I have it graph from 0 to 4 pi? Oh, look how pretty that is. What if I went to 6 pi? That's not some, well, now you saw the rectangular equation for that, right? It's not attractive. This goes on and on and on because theta is going to grow without bound, right? So your radius is going to grow without bound. Isn't that crazy? Isn't that pretty? Yes, there are lots of things in nature that are modeled with this form, right? That is called a spiral. All right. Keep your calculator out. And let's do this one. Convert these equations to rectangular coordinates. So, what do I do here? Think about your equations. This is so tantalizingly close to x, isn't it? And I'm trying to go to x and y, an equation with x's and y's, and this is tantalizingly close. I know I can write the square root of, right here, r is equal to the square root of x squared plus y squared. But what do I really need in here to take that into an x? I need an r. So how about, back up, how about you do something from Algebra 1? You have an equation, so do whatever you want to one side of an equation as long as you do the same to the other. I think I will multiply this entire equation by r. And then what do I get? Oh, hello, x. And this time I don't have to have a square root. Woot woot! Now, before I go on, let's do this one. Can you see that you're going to need to do the same thing here? I recognize I've almost got a y. I need an r, so see what you want and legally make it happen. And say, oh, hello, y. So these are two equations that you have gotten into rectangular form. But oftentimes you are going to be asked to get those conic sections into graphing form. So we have to go back and pull out our little book from AAF and say, what did we do to get this into graphing form so we could identify the shape? This problem, if I just said convert, you are done. But what if I asked you to identify? Or you were doing matching, okay? So, from Algebra 1, you got everybody over onto one side, and then you had to complete the square. Now, this has to be fast. This is why you did this, hopefully, in an Algebra 1 class. And maybe in geometry, I think they did in Common Core geometry, I think you did some completing the square. I don't need to do anything with the y's, but be careful. Remember, you have changed the right side of the equation by adding a 4. So you need to change the right side of the equation by the same amount. And again, if you don't remember, you don't remember completing the square, you've got notes on it, you've got examples, that's why it's important to keep notes. Of course, completing the square is rusty. You divide this term by 2, you get 2, you square it, you add that here, and you add that here. Make sure there's nothing to multiply out front by, and then good F word, you factor that. It's x this sign, and then b divided by 2. And now you should be able to identify, because A and C were the same, you knew you had a circle. Now that you've completed the square, you know that this is a circle with a center of -2, 0, and a radius that is equal to 2. So you can imagine we're going to do the same thing over here. Where this time we collect the y's, complete the square, you knew up here with A being equal to C, you had a circle. But now you know you have a circle with a center of 0, 2, and a radius of equal to 2. Now, if, again, you are just asked to convert, you can be done here unless the directions specifically tell you to get it into graphing form. But if you're asked to identify, you might not know, hopefully from conics, you know with A and C equal to 1 that you've got a circle, but what kind of circle? So what if you were asked to identify what you have, or if you were asked to match a graph, which is like what your part of your homework is tonight. If you were asked to match, and I gave you this graph, which one is it? Right? As soon as you got into rectangular form, you might hopefully be able to see, well, this is a circle with a center at 2, 0, and a radius of 2. So that's that graph. So what do you think the graph of 4 sine theta looks like? Well, you don't have to think at all, right? I just gave it to you, right? Or you just did the work, right? This was a circle with a center at 0, -2. I'm sorry, 0, 2, and a radius of 2. Now my circle's going to not be nearly as pretty as this one. Radius is equal to 2. And go to your calculator and check. In your calculator, put 4 cosine theta, and you're going to see this graph. And if you change 4 cosine theta to 4 sine theta, you're going to see this graph. Now, with experience, what if you are not asked to convert? You are just asked to identify, or maybe even more helpful, match. If you are just asked to match, and you want to save some time, it is worth your while to maybe say to yourself, hey, what if I don't want to go all the way to rectangular form? I'm just giving these 2 equations. I want you to remember about your unit circle and cosine. Coordinates on the unit circle. Who did cosine go with as opposed to x? Didn't on my unit circle, wasn't cosine an x thing? Right? It was always the x coordinate. And who did sine go with? Sine always was a y thing. I want you to look at those 2 circles. This circle is oriented x. It's an x thing. This circle, its radius, right? Radius, I mean, your radius is in all directions, so I don't say, but can you see it's on the right x side? This one is, right, can you see the y thing along the y-axis? This is along the x-axis, right? Right, it's symmetric around the x-axis. This is symmetric along the y, right? I say this is oriented y. Hey, if you have your calculator out, what do you think the circle looks like? How about -4 cosine theta? What would that look like? Oh, snap. It looks like that. What do you think -4 sine theta looks like? Oh, snap. It looks like that. Now you can do the algebra and verify it with this and this, but if you are not asked to convert, you were just asked to match, right, or identify, hello, when you work with these equations enough, you start to pick up some patterns, and it does all come from the unit circle. Speaking of the unit circle, you remember after we learned the unit circle, we learned how to graph. Now forget that this is in polars for a second. Remember, I'm not asking you to convert. Forget that this is in polars. What if I just gave you that equation and in rectangular form, and I asked you to graph it in rectangular form? Not the circle. I asked you to graph y is equal to 4 cosine theta. In other words, I asked you to jump off of the circle. And just going from 0 to 2 pi. Right? Remember our 5 critical points, our start and then our quarters. Oh, that's so bad. So bad. But here is my minimum. Here are my maximums. At 0, pi over 2, pi, 3 pi over 2, and 2 pi. This circle is going to be, when you input 0 for theta, you're going to be at 0, 4. Where do you think you're going to be at pi over 2? 4 times cosine of pi over 2. Where do you think you're going to be when theta is pi? Right? Can you figure out where you're going to be all along this circle? Let's get out your calculator to verify. Four cosine theta. Go ahead and hit trace. Hey, what the heck? Do you see my little worm still going there? What is happening? Why is it graphing so long? Oh, remember what I made my window? 0 to like 6 pi? So when I was asking it to graph it, my grapher was spinning around that circle a gazillion times, wasn't it? Whoops, I might run too far. Zero to 2 pi, 0 to 4 pi, 0 to 6 pi. Whoops, sorry, I didn't count right, did I? Oh my gosh. Wait, so going all the way around was not 2 pi? What's happening? Wait a second. Let me go make this, if I hit zoom 7, remember that, well, zoom 7 goes, goes, let's see what zoom 7, 1, 2, 3, 4, what is happening? Wait, it's still spinning just as much. What is going on? Oh, zoom 7 just makes me go from, right? It didn't change my theta. All right, so things are going to be fine here, right? Everything's going to be fine. I'm just going to go around once now. Boom. Oh, wait. What? What? What is happening? All right. Theta is 0. X is 4. I expected that, right? You're putting, right? Cosine of 0 is 1. 4 times 1 is 4. Now what happens as I rotate through theta? Oh, I thought that was a pi over 2. No, silly. What is that? Right? What is, right? Cosine of pi over 2 is 0. So that's not going to get me up here, right? So this is a common misconception with looking at a rectangular graph, right? And there are some similarities, but you do have to be careful, right? Look at x and y. X and y is 2 comma 2. That's at a 45-degree angle. The theta is pi over 4. Pi over 2 is over here, isn't it? Right? When theta, if I hit trace, theta pi divided by 2, there's pi divided by 2, 1.57-ish. Now if I keep going, right, this is going to be 3 pi over 2 when I'm at 2 comma negative 2. And what is this? What is my theta? My theta is pi. My theta is pi, and I'm back at 4 comma 0, so that's why you trace it again. Crazy, isn't it? What if I wanted the calculator to only graph one time around the circle? How would you change your window? Bam, right? So polars are, right, gotta be kind of careful with your thinking and what's going on with these graphs. Now let me once again, let me go back here and say what graphing this in rectangular, right? Graphing not on polars, stretching this out. Right? When theta is equal to 0, I'm up at 4. When theta was equal to pi, I wasn't at negative 4 though, right? On my circle, remember? The x-coordinate here was 4 comma 0, but on polars, right? In polars, this was r is equal to 4, theta is equal to 0. We were thinking this was pi over 2, but it's not. This is pi over 4. This is when theta is pi over 4. This here is when theta is equal to pi. I'm back at the pole. This is when theta is equal to 3 pi over 4. And then this is also, I'm coterminal here when theta, this is when theta was equal to 0, but also theta was equal to pi. Look at my graph, my rectangular graph. That didn't go so well. Can't really tell the difference, can you? Well, that's kind of crazy. But remember, that doesn't really match up. But remember, this is my rectangular coordinates. I still am, right? So while I'm bouncing back and forth from positive to negative in rectangular land, here I covered one whole circle by just this, right? That was this circle. So I was trying to match up what was going on in the wrong times. common error. So look just at this part, right? And again, let me go back and draw the whole thing. It's again a terrible looking graph. Let me go back and just go to pi. Look at what's happening when I just go to pi. Because one time around the circle, I wrote pi over there, didn't I? Gosh darn it. Sorry, it's what happens when I'm trying to... If I only go to pi, hey, positive, negative, hey. What happens then when we actually made our calculator go all the way to 2 pi, when we made our calculator go to 0 to 2 pi, what happened? Didn't we travel this again? Right? We went 0 to pi over 2, and then to pi. Then we went around again. Crazy, crazy. Right? So be careful with your window and what's going on with your, right? Thinking it is good to think about what this looks like in rectangular form and thinking about how I go back and forth across the x-axis, what my maxes and my mins are, and how that correlates, my start and my stop, and how that correlates with this graph. Right? Notice I never had an r that correlated with -4, right? My radius, because my radius is always +4 here. So don't, right? Be careful with that. All right, let's go to this one. Convert the equation to polar coordinates. This is going the other way. How are you going to deal with this? Again, Algebra 1, you want this to be quick. Can't spend time multiplying that out. Now what do I need to go to polars? There's my r, isn't it? Oops, sorry, that's a y. And then +16, +9 is +25, subtract. And I get 0 over here, right? So technically +0. Now, what can you replace this with? And this. And this. Whoops, I'm sorry, I forgot my r. Done and done. Now, from AAF, you know this is a circle, right? Because there's no, right? Rx and Ry are the same. So it's a circle with a center what? And a radius of what? When I go to my calculator and I plug in I'm sorry, first I have to, right, my calculator is only in r, right? So remember, I got r squared, which is fine to leave it for if I just asked you to convert. and you left it this way, that is perfectly fine. But for my calculator, I need r to be by itself. So I just divide everybody by r. Usually dividing by a variable is tricky, right? But because you lose a root, but r equals 0 is a solution as well, and it's on the graph. So, and I really only care about doing this if somebody makes me get r by itself or I need to use my calculator. So let's put this into my calculator. So again, as soon as I went to r, realized, oh crap, I can't put r squared in there. So I have -8 cosine theta plus 6 sine theta, and I hit graph. What is that? Oh, right. See, this is why it's important to kind of think about what you should get. This is a circle whose center is at -4, 3. I don't, -4, 3 is here, so the center is like here, right? And a radius of 5 from that, I don't see it all. So I need to go adjust, right? So maybe, what if I make this -10? And I can leave that. And I can leave that, but maybe I make this 10. Let's see if that works. There we go. Now it doesn't, with my pixels, it doesn't look so much like a circle, but this center is -4, 3, and the radius is 5. Right, and here I can travel around my theta, and I can see my x and y coordinates. Remember, you can, if you don't, you can get the polar coordinates here and get the actual values from your calculator. Oh, why aren't I going farther? What's the matter? How come my calculator's broke? Oh, remember I made my theta only go to pi over to pi? That's as far as I can go. But that was one travel around the circle. Crazy. All right, next. Oh, boo, boo. You're going to learn that these equations, when they ask you to convert, are super annoying. You would much rather just be asked to match or to identify what this is. For right now, all you can do is convert. Do you see what the issue is? Well, if I certainly can multiply by r like I did before, but this is the issue, isn't it? Gosh darn it. Now, let me think about this again. Let me do this kind of graph in rectangular, right? Pretend that's a y, and I asked you to graph 6 cosine 3 theta. Certainly you know your amplitude is 6 and -6. Now, in AAF, what we did was we focused on this b value, and we said we only wanted you to graph in a distance of 0 to 2 pi, so you had to figure out, right, what your period was from that. But do you remember I first taught you what that 3 meant on your graph? Do you remember? B literally is how many cycles of your graph you see in a distance of 2 pi. So cosine theta, right? how many cosine thetas am I going to see in a distance of 2 pi? 3. Now this is going to, no judging. I've got to fit one cosine graph in there. Oh, Lanta. One here and one here. 3 cosine graphs in a distance of 0 to 2 pi. All right, now let me go and get this into rectangular form. So unfortunately, what you are going to have to use is an identity to expand this. Now, I don't expect you to remember, and we didn't test you on, in the first semester, the identity for 3 theta. This is why I did this in class. I wouldn't put this on a test, but here is what it is. Ah! And I have to look at it as well. I don't remember this very well. I don't use it that often, so you know it can't come up that often. Now I'm going to do some algebra with this. And again, sorry for the sloppiness there. Cosine 2 theta, cosine theta minus sine 2 theta, sine theta. Now I'm going to use some more identities. I'm going to use an identity there. And I'm going to use an identity here. These identities you should know. Cosine 2 theta, you were responsible for that identity. Now remember, this was the annoying one that had a bunch of different forms. This one, sine 2 theta, was pretty consistent, right? So I replaced cosine 2 theta with cosine squared minus sine squared. Oh, Lance, I didn't leave enough space. I still have a cosine theta and a minus. I replaced sine 2 theta with what's in red, but then I still have a sine theta here. So now I'm going to distribute, and I have cosine cubed theta minus sine squared. Right, I'm distributing here. Minus, and I'm going to distribute here. And now I am going to multiply, and again, I would not, I did this on a lesson, right, because I wouldn't expect you to come up with this on your own, but I am going to multiply everything by r cubed. You do not have, none of your homework problems are like this, but there are a few of your homework problems where you do need to use an identity, and I've given you a hint on the handout when to use that. So that's the piece that the handout is for. None of your book problems require that you use any identities that I can remember, but a couple of the handout problems do, but not this one. So this ends up being r to the 4th on this side, and then I end up getting 6r cubed oh, whoops, I'm sorry, I forgot to clean this up a little bit before I did that. I forgot to clean the blue one up. I apologize. Let me go down here and clean this up a little bit. You see what happened there, right? I have this cosine cubed. I have a minus sine squared, cosine squared, and minus 2 sine squared, cosine squared. So that's where that 3 came from. Now I'm going to multiply everybody by r cubed. And distribute the 6. So this becomes 18. Ah. And what do I have here? Remember, I can replace r squared with something. Well, isn't r to the 4th r squared squared? And then what is this? Isn't that just, right? Since that's a product, isn't that r cosine theta cubed? And what is this? R cubed sine squared cosine squared. How can I rewrite that? Well, one of those r's is with cosine theta, and the other 2 r's are with sine squared theta. So isn't that x? And what can I do with this? That's super annoying. And again, I would not expect you at this point to have to do that. I just was showing you some algebra manipulations. The identity ones you have to do are not this bad. But I need to, again, focus on the fact that in rectangular form, this is gross. What the heck? I guess I could again, I mean, there's not much I can do to make that much nicer in rectangular form. Look at how clean and nice this looks in polars, right? In polars. Now, again, don't think that this, sometimes I hesitate whether I should think about that. This is not this equation. They are not the same thing, because I was just graphing y is equal to 6 cosine 3 theta. That is not really the rectangular, right? I was just picturing in my head what this is saying to do. This green equation is the rectangular form of this equation. So the thing is, we haven't really looked at the graph of this yet. In polars. So now think about what that green equation looks like. That's the graph. So the green equation this equation will generate that pretty looking graph. But notice this graph ain't a function. I could kind of tell that from here. You're going to have a lot of trouble plotting that in rectangulars. Now I purposely left the axes off this one, because I want you to go ahead and put this equation into your calculator to get this graph. So when you hit 6 cosine 3 theta, Can you get my picture? And I want you to go ahead and look at the axes. Now remember what I was trying to tell you before with orientation. What kind, do you see any orientation here? Yes. Right? Can you see the axes? Right? Here's the pole. Here is the positive pole. And look at this petal of the rose. Yes, we're going to call this a rose. Doesn't really look like a rose, looks more like a flower, but what can we do? I didn't name it. Isn't that kind of sort of an X thing? And notice who was in your equation. Now again, let's talk about not the rectangular form of this equation. I just want to talk about what, if I stretch this out, y is equal to 6 cosine 3x, what that looks like. Right? So when you hit trace on your calculator, you should be at theta equals 0 is here. Right? And that should make sense. If you put 0, 3 times 0 is 0, cosine of 0 is 1, 1 times 6 is 6. Right? So you're out here. Then when you trace around, to this part of the petal, right? Where do you go after that? So just trace along, all right? I'm trusting you're doing this with your calculator. When you trace along, you're moving along that first petal, and then where are you going? Then you go here into right? So this is the path that you're following. You should be at a radius of -6 here. And if you follow your cursor, you come back to the pole. Think about what values that would be, right? So pi over 2 right? What happens when I put pi over 2 in here? I get 3 pi over 2. Cosine of 3 pi over 2 is 0, right? And if I keep going, follow your cursor, right? Are you going with me? Trace, 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 trace. Back out to a radius of 6. Where do you go? Coming back down the other side of the petal. And then finally where? What theta are you at? Again, you're at theta equals pi. So how many times will you trace this entire polar graph in this distance of 2 pi? If we think about this 3 down here meant 3 cycles in a horizontal distance of 2 pi. But that doesn't correlate up here, does it? Up here, how many times did I trace my petals? I only trace my petals here. In a distance of 2 pi. Well, that's weird. What does that 3 mean then? I see what the 3 means when I stretch things out here, but what about when I'm graphing on my polar grid? What does that 3 correlate to? Hey, hey, wait a second. Whoops. How many petals do I have? Oh, my Lanta. That's how many petals I have. Well, then this should be easy. Radius of 6, so I know how long each of my petals are. Right? So the 6 gives me how long the petals are, and oriented cosine, so that petal goes like that. So each petal is a length of 6. And I've got 3 petals because I've got 3. Well, so this should be easy. Does that work here? Do 6 sine. Oh, what do you get? I'm certainly not going to make you put any of these in. I'm not going to ask you to convert. Can you just see the pattern though? Hey, this is a Y issue, so can you see where you're oriented? Now, this is a little confusing because do you see the orientation is here? One of my petals goes like this, but my petal length is still 6, and then my other petals it's terrible. So I certainly see the Y orientation there. I just was expecting it to be positive. But use your trace, right? And can you see if you can tell why that is? My petal has a length of 6. And what about the tracing? Can you see the direction that it traces? Use your trace button and go around. And you do trace negative. Again, sine, 1, right? What does sine do? There's my graph of sine stretched out. Positive, negative, positive, kind of, sort of, right? Patterns. And notice again, I have 3 petals. Play around. What happens if you do make this negative 6 sine 3 theta? Okay, it's the opposite of what I thought. Okay, that's slightly annoying. That negative 6 sine theta kind of goes in the positive y direction, but whatevs. I can deal with that. How about the negative 6 cosine? That follows more what I thought was going to happen. Sine always giving me trouble. There's my negative cosine, and then my 3 petals look like that. Do not want you to get that in rectangular form. The rectangular form is ugly. Pretty graph, pretty equation. Oh, these must have 2 petals then. My pattern is to continue. So change the 3 to a 2. Wait, what? Crap. What does this graph look like? It doesn't have 2 petals, gosh darn it. Cosine is an x thing. So, and my radius is positive, I expected this petal. But you know what I got? I got this petal too. And I got this petal too. And I got this petal too. So my kind of orientation pattern kind of blows up here. Well, what the heck then does 6 sine x look like? The same thing, do you think? Oh. Weird. 6 sine 2 theta looks like this. There's no orientation with an axis. Everybody's kind of like at 45. Oh, this is so, so terrible. There's a reason why I wanted you to use your calculator to do this. OMG, Miss Getz, I'm so bad. The point is, though, I didn't get 2 petals. I got 4 petals. Now, I've been just kind of playing around. We are going to do more with these equations. I've been going back and forth. I've been, on polar coordinates, rectangular coordinates, been like, oh, this is wrong. Oh, I thought this was going to happen, and it's not going to happen. I just want to encourage you to play around with these. Think about your graphs of your graphs. This is not rectangular form of the same equation, but kind of think about what your periods are, where your positive and negative increasing things are, what that means for your roses, right, and your petals, whether you even have a rose or a petal. Remember, in the previous slide, we had just pure circles. When does that happen, right, and why? So none of this is going to be obvious right away. It just takes exploring and discovery with some of these things. I took you through this conversion from polar to rectangular with these. Trust me, not a focus going forward. Yes, your basic graphs you need to be able to convert your circles, your vertical lines or whatever, but not these. You're going to be working with these in polar form, and I don't ever want the rectangular form of these more complex polar graphs. You're just going to need to know kind of sort of what they look like, but we're going to go into that more. Your homework next week, your homework is just practice converting, and the handout take as simpler identities than this 3 theta.